Okay.
Awesome. Okay, so today is our last lesson of the course. And for the last lesson, we're going to see a full dApp developed. So we have a front end. We can optionally have a backend if we want, or just do everything in the front end. In our case, we're going to do everything in the front end because we want to actually interact with the blockchain, with the stable coin, with the example as all parties. So, but in a real scenario, we will put part of the logic in the backend and part in the front. So in the backend, there will be the part that developers use, run, and in the front end, the part of the users. But we're going to put everything in the front end so we can actually use it, right? So we're going to build a stablecoin, both the actual contracts and the way the off-chain code to interact with it. So first, let's talk about stablecoins. Let me share my screen. Okay, 1 second, 2 seconds, 3 seconds. Okay, now it should work. There you go. So a stablecoin is a token that lives in the blockchain that tracks in some way a stable asset that is usually outside the blockchain, because like blockchain is volatile, but people in the real world have, not in the real world, but like in the standard economic world that we have today, we use fiat money. We use money issued by governments. So we have the US dollar, euros, shillings. We have like different coins, and these currencies are regulated by governments, and they try to maintain it as best as they can stable. But the thing is, even if they do or they don't, the population of that country needs to use that specific, currently needs to use that specific currency to buy goods and services. So, and what we want is to track a fiat money, a fiat currency, sorry, to maintain a token on the blockchain that is worth the same as the currency issued by some other entity outside the blockchain. So that has like several reasons why, but the most important, and I think the overarching idea, is that we need a way to connect the blockchain money with fiat money. Where currently we use fiat money, we use like currencies issued by governments to like buy stuff. And if all we do with blockchain is like to buy and move tokens around and move PDFs around, and there's no real connection with buying goods and services, then it's not going to be really a way to replace, or at least in part replace, fiat money. So that's the main overarching idea of adding the concept of a stable coin to blockchain, is to connect the value of the blockchain with the value of the rest of the outside world, let's say it like this, and to provide, of course, some asset that people don't need to quickly act to to avoid losing money or whatever. Like anyone that has a stable coin that's attached to US dollar can say, okay, I will just turn my ADA tokens or Bitcoin tokens or whatever to USD tokens. And I know that those are going to be worth the same as the US dollars. So I can just let them sit there for a while until I make decisions about what I want to do with it. I want to buy something else, change tokens, whatever. So stable coins are really the key to connect the fiat world with a token blockchain world. And today there are several ways to create a stablecoin. And in our case, so one way which has been used in the past is to say there's a centralized place, there's a centralized company or entity that promises to have, for example, let's say that we want to attach our token to US dollars. So this company has a way to mint and burn these tokens, and they, in some way or another, that could be either like just pinky promise, or it could be like actually going through some sort of regulation or steps to prove that they are actually putting in a safe the same amount of money that they are minting, and that the money that is locked is in sync with the tokens that have been minted and burned. So that's one way, but that way requires a centralization, requires we need to trust one or multiple, but a small number of centralized entities. That could be a government, could be regulatory entities, could be companies, or all of the above. Another choice is to use an algorithmic stablecoin. The main difference is that instead of having this entity that has full power, full control over the minting and burning process, there's an algorithm. So there's no one in charge. There's no specific person that handles the minting and the burning, but there's an algorithm that, if it's built cleverly enough, the algorithm incentivizes users of the stablecoin to mint and burn in a way that the price of the token maintains or keeps a really, really, really close value than the asset that it pretends to track. So in our case, we're going to do an algorithmic stablecoin. We are going to implement the algorithm of the stablecoin in the actual validators. So there's not going to be anyone in charge of that. There's going to be a stablecoin deployer. So like the stablecoin developer that is going to deploy the stablecoin. But once that stablecoin is deployed, the developer, or actually no one else, can do anything about, cannot control how the stablecoin is issued or minted. That's hard coded in the logic of the contract, cannot be changed. So that's an algorithmic stablecoin. If anyone has any questions, please interrupt me.
Just wanted to,
yeah,
I don't have a question. I just have a few remarks. I mean, first of all, I mean, Ethereum is famous for its stable coins, in particular USDT and USDC. And they are like of the first kind that you mentioned. So they are not algorithmic. There are people basically deposit actual US dollar, and then for each US dollar that's deposited, more or less, one of those coins is minted on Ethereum. But so, I mean, that's the first thing I want to say. So that's very popular on Ethereum. One thing is that those companies, I mean, I'm not sure about USDT, how exactly it works, but I think both of them, USDT and USDC, they don't just leave the US dollar that have been deposited like peacefully sitting around in a bank account. They invest that. I mean, that's how those companies make money. But that, of course, also means there's a certain risk. If they make a bad investment, then maybe the backing US dollars are gone and people then can't redeem their USDT or USDC for US dollar anymore. So that's the first remark I want to make. Then the second is that very recently, like 2 weeks ago or so, on Cardano, stablecoin of that kind launched, USDM. And they are not algorithmic. They are backed by actual US dollar, but they are different to USDT and USDC in that they don't invest the money. So they guarantee or promise, and I think it's like also heavily regulated in the US, that if somebody deposits $1 on a specific bank account, then the corresponding USDM is minted on Cardano, but they don't touch that money, so they don't invest it. So it has the potential to be much more reliable than USDC and USDT. Okay, that's the second thing I want to say. And the third thing is here, potentially on Cardano, stablecoins could be much more like valuable or successful than they are even on Ethereum, because Cardano has actual native tokens. On Ethereum, they don't. The only currency on Ethereum is Ether. And these tokens that everybody is talking about, including stablecoins like USDT and USDC, they are basically just a fake. They are implemented with a smart contract. And the way it works is basically, it's just, somewhere on the Ethereum blockchain, there's the Ethereum blockchain has like global state. And somewhere there's state, it's like a dictionary from accounts to numbers. And if Robertino, for example, owns 100 USDT, then in this dictionary, there would just be an entry with key Robertino's address and value 100 USDT. And if he transfers $30 to Karina, then all that happens actually on the Ethereum blockchain is that this dictionary is updated. So then 30 are subtracted from his entrance in this dictionary and 30 are added to Karina's. But it's completely different mechanism to how Ether works. So Ether is one thing, but these tokens on Ethereum are completely different. They are implemented with these dictionaries. And one consequence is that depending on the smart contract that governs these dictionaries, Ethereum can do all sorts of weird stuff. A lot of tokens on Ethereum work as you would expect it to work. If you have an Ethereum ERC20, so-called ERC20 coin, in your wallet, you have it. And you can decide what to do with it. But that's not guaranteed. The smart contract that is in control of this dictionary can do whatever they please. So there are like weird coins on Ethereum that, for example, every day at midnight modify the amount. So you go to bed and have 100 of those coins, and then you wake up the next morning and suddenly you have 200 or 50. So that's one thing. And in particular for the discussion of stablecoin, in particular USDC, and I think USDT as well, they can do that. So they have like a deal with the US government that if you end up on some terror list, blacklist, they can basically take the USDC or USDT away from you, just like that. So even if you have them, you're not guaranteed to keep them. And there it really makes a difference that on Cardano we have these native tokens. Robertino explained that very nicely, was it like 2 lectures ago, how this works. So the minting and the burning is controlled by a smart contract. But once you have the coin, it behaves exactly like ADA. In particular, nobody can take it from you against your will. So there's no way that you go to bed and wake up and have a different amount in your wallet than you had when you went to sleep. So that means potentially stablecoins on Cardano could be much more reliable than on other blockchains, in particular on Ethereum. I don't think any of us is a terrorist, but nevertheless, I think it's sort of comforting that that no government or anybody can take your money away while you sleep. So potentially that's a big thing. And as I said, so until now, I think we do have this chat thing. So we do have an algorithmic stablecoin in Cardano, but somehow that never really took off. And
There's
now since
Indigo as well. So there's a few. There's Indigo as
There's-
well. Yeah.
right, but I think none of them is really very successful for whatever reason. And I think this USDM now that launched 2 weeks ago is the first. I mean, it's the first non-algorithmic one. I think. I'm not sure how Indigo works, but anyway, it seems. I mean, this is like looks at the moment. It looks quite promising, this USDM thing. So let's see where it goes. But I mean, that would be nice to have a stable, a successful, reliable stablecoin on Cardano. And as I said, once we had that, it would be even cooler than on Ethereum because of what I said. Nobody can take it from you. Yeah, that's what I wanted to say. Sorry for interrupting.
No problem. Thank you so much, Lars. So yeah, that could be you, maybe. Like that could be any student of this course could actually like use their knowledge and develop a nice algorithm and take the stablecoin market in Cardano, maybe. So, in this case, we said that we're going to do an algorithmic stablecoin, and it's a specific kind of algorithmic stablecoin that is called over-collateralized algorithmic stablecoin. So, the algorithm has a system that is usually actually I'm not sure if there's a different possibility, but as far as I know, there's the over collateralized depends on the liquidation mechanism, and this liquidation mechanism is the incentive that the users of the stablecoin will have to mint and burn in a way that the stablecoin maintains its value close to the real asset that is trying to track. So, how are we going to implement our stablecoin? We will use 4 different validators, but the one that like really matter, the one that hold the logic of our stablecoin, are just 2. One is called collateral validator. This validator is the one that is responsible of locking the asset of a user and like release them in when it should. And this collateral this collateral is the value, is the asset that gives the stablecoin the value. So it has to be made in a specific way so the value locked in the collateral tracks the real value of the asset that we want to track. In our case, we're going to lock ADA, but there's no restriction in that because, as Lars just said, like they are native assets in Cardano could like be interchangeable with ADA in this regard. So we're going to lock ADA in a validator called collateral, and we're going to mint and burn stablecoins using a minting validator. So those 2 are the ones that are going to hold the logic of our validator, and those 2 are almost always those 2 are in almost all scenarios running together. So we're going to see like diagrams now, but this is just like a high-level overview. And these 2 validators, I think we didn't saw yet an example of running 2 validators at the same time, but we already said that it's possible and that it's not like a big deal. So we're going to run them in parallel, and they are going to check. They're in between both validators. All checks are going to be run to make sure that we are able to mint and burn whatever we want to print and burn. And so let's see. I'm trying to think if I'm missing something. I don't want to forget some real important. Yes, so over-collateralize here. Over-collateralized means that we are locking in the collateral validator, we are locking more value than the coins that we are minting. Why are we doing that? Why are we not locking exactly the same value? Well, because the extra value that is locked and is not minted is what someone else is going to get if they liquidate your position. So if you create, you mint your stable coins. Let's see if we have an example somewhere. So liquidating, let's see, I'm going to just follow this.
I just wanted to say, I mean, that's all true what you say, but I mean, like the high level idea is that the price can change. I mean, we use ADA as collateral, and ADA is, as you said, very volatile. So I mean, let's say, just for argument's sake, right now, I think it's, I don't know what it's worth now, but let's say it's 50 US dollar cents at the moment. I think it's more, but never you mind. So if you want, I mean, that means if you want 1,000 US dollar, you would need to use 2,000 ADA as collateral. But the problem is that, I mean, the idea is that the stablecoin is backed by this collateral. So that's what gives it value, that you know you can always like exchange it for the collateral. But the problem, of course, is what if the price of ADA goes down? I mean, if it goes to 40 cents, for example, then, I mean, the 2,000 ADA that were deposited suddenly are only worth 800 US dollar, not 1,000 US dollar anymore. So if you minted 1,000 US dollar and only collateralized it with 2,000 ADA, and then the price of ADA goes down, then suddenly some people wouldn't get their money's worth if they exchange it back to ADA. And that's why you over collateralize. I mean, that's a high level reason. I mean, the mechanism, as Robertino will explain, I mean, there is a clever, like, game theoretic mechanism to actually implement that. But the idea is you just must like give a buffer so that even if ADA price falls, it's still enough to give everybody their money back. Of course, if it falls dramatically very fast, that's still a problem. Therefore, this over collateralization must be set quite high, like twice. So maybe you would have to deposit 4,000 ADA to get 1,000 US dollar. So then even if ADA loses half its value, it's still okay. And then there's enough time in between for people to react and do whatever Robertino will explain to us now, what they can do. Sorry.
Exactly. Thank you, Lars. Thank you so much. So liquidating means burning the same amount of stablecoins that someone else minted. So not your own stablecoins, but someone else minted. But if we could do that all the time, like no one is going to lock anything because you're going to lose money every time you lock something because someone else is going to unlock it. So for that, the algorithm it's going to allow you to liquidate someone else's position only if the relationship between the value of their locked collateral and the stable coins that they minted is within a certain predefined threshold. And this threshold can be chosen by from the developer from the get-go, and once deployed, it's going to be, and at least in this implementation, it's going to be fixed forever. So let's say the threshold is 150%. So, and if the value of ADA is $1 US, that means that if you want to mint 100 US dollar, you have to lock 150 ADA. So we are locking 50% more than what you're getting as value. And then if the value of ADA drops, like Lars just said, if it drops, for example, to 130, if it drops in a way that the amount locked now is 130% instead of the threshold of 150%, now anyone can burn their stablecoins by liquidating your position and they are going to get 130% the value they are giving. So they are earning 30% on top of what they are putting. So they have the incentive to liquidate anyone's position that is below the threshold that the validator allows you. If the price of ADA goes up, the validator won't allow anyone to liquidate your position. But the thing is, you could mint more without putting more money. That you can have more stable coins with the same amount of collateral. So now you have the incentive of minting more to get more worth for the same amount of value locked. So that's how that's how the algorithm tries to maintain the price, trying to maintain the value pegged, as he said, to the actual asset. If it goes down, someone can liquidate your position, so you have to put more value locked, and that makes the asset, the amount of value locked makes that the asset, the stablecoin price goes up, so that it restores to the initial value. And if it keeps going, if the price of locked asset, in this case ADA, goes up, and if you don't do anything, the price of the stablecoin is going to go up. But you're going to have the same amount of stablecoins, but you want more stablecoins because you can get them because you already have more than enough to pay for those stablecoins. So you're going to mint more. And then because people around the world are going to mint more stablecoins, the price of each stablecoin is going to drop to the initial value. So that's how it's going to be maintained around the value, assuming everyone is a rational entity and everyone is relatively up to date with the price. The thing is, this could go wrong if the value of the locked collateral goes down, the value of ADA goes down so fast that people don't have enough time to liquidate other people's position before the percentage of the locked value goes below 100%. So why is that an issue? Well, as we said before, we have the incentive of liquidating people to get the extra money of the locked collateral. But if now the collateral is below 100%, that means that I have to burn more stable coins that are worth more than the unlocked collateral that I'm going to get back. So I will prefer just to not do that and just keep my stable coins, and I will have more value than if I would do the conversion. So I won't do that. And that means that if I'm not replacing the collateral that now is completely unpegged, now has not worth what it should be worth, and no one has the incentive to fix that, it means that the stablecoin will crash into zero and is going to be worthless. So that's a huge problem. And that's why many of the algorithms don't use 50% on top of the value and use more complicated schemes and algorithms using multiple coins and using not only 150% of collateral, but 400% or 800% over collateral. So there's so much collateral that if it drops below, it has to drop an insane velocity before someone else wants to liquidate a position. And that means that it's way more likely that it doesn't drop at that huge rate, and people are actually going to have enough time to liquidate others' position, and the stablecoin is going to keep being stable. So that's high-level overview of how the mechanism works. Now, I mean, anyone has any question about like this overall idea? Now I'm going to move into actually how we are going to do the transactions, which may be going to help a bit with the concepts, but anyone has any questions?
No, in the chat.
Thank you so much. So, one thing that I forgot to mention is that if we do this, if we do like all this mechanism, we need a way. We said that we will need to calculate the collateral based on the price of the asset we want to track. But if we had the asset that we want to track in the blockchain, we wouldn't be creating the stablecoin from the get-go. So if we had USD, if we have dollars in the blockchain, we wouldn't need to create the stablecoin for starters. So we need a way to get the information from the outside world, and we already saw last lesson how we do that. We use an oracle. So we're going to have an oracle that is going to provide us the current price of ADA in USD, and our stablecoin validators are going to consume that information to make the decisions of how much can you mint, burn, and if you can or cannot liquidate. So that's the bridge. The oracle is the bridge between fiat and blockchain, and then the algorithm use the oracle, the information provided by the oracle. So let's see. Let's deploy the stablecoins. What these are transactions. The circles are UTXOs, and the squares are transactions. So we start by deploying the oracle. This is the same thing that I explained like the other day, but with extra steps, doing one thing at a time. So the stablecoin developer wants to mint an NFT, and then with that NFT, is going to deploy an oracle, and then the oracle validator is going to have in its value an NFT, and in its datum is going to have the USD ADA rate. We already saw this last lesson 2 days ago. So this is just the same exact system that we explained in detail in the last lesson. In our case, we say here, like this is the stablecoin developer's wallet, but this actually is not the stablecoin developer, but it should be, at least it should be, some other oracles, like some trusted system of oracles, because if the stablecoin developer controls the price of like unanimously controls the price of USD ADA, then like that stablecoin developer is like centralizing control, so they can just increase and decrease the number to liquidate people's position, and they have like complete control over everything. So the actual oracle, we are deploying it ourselves because this is just like a test, an example. But the oracle should not be controlled by a single entity, because at that point, that single entity controls the stablecoin, basically. So first step, we deploy an oracle with, in its datum, the value of USD and ADA, USD ADA rate. Then we deploy the collateral validator and minting policy. This is new. This is the first time, I think, that we actually use reference scripts. So what are reference scripts? We saw in previous lessons that every time we need to consume a UTXO from a validator, we need to provide the script so the node that validates the transaction can actually run the script and make the checks that it needs to make to know if it can unlock the UTXO. The thing is, this is really costly, both for the blockchain overall, because every time you create a transaction with the same validator, you have to upload the same, like you have to send to the node, and the node has to register the same validator dozens or hundreds of times through the use of the blockchain. That's one wasted amount of like calculation, RAM, and space. And another thing that happens is that it's more expensive for the user because the user has to pay for the transaction, and you have to upload, you have to send in the transaction the actual validator, and because the value, the fee that you pay per transaction is based on both the size of the transaction and the computation units of the validators. That means that the user is paying more money for, not more money, the user is paying a lot of money. So how can we reduce the amount of money that the user is paying? So what we can do is we could send the actual validator, not the address, not the hash, but the actual like byte code of the validator to a UTXO. We can attach the validator to some random UTXO that we want to attach it to. In this example, we attach it to the always false validator that we saw in lesson 1. So a validator that cannot be consumed. And this is because we, in principle, we want to assure the users that no one can like remove the collateral validator and all of a sudden you cannot use the stablecoin. So you send it to this specific always false validator address that everybody knows that nothing could be consumed, no UTXO can be consumed from there. And you attach the validator to that UTXO, and that means that you can be sure that it's going to be there in that specific UTXO forever, and you can use it in your algorithm. That's in principle. In practice, what we're going to do is, because if we do this, then like when you try the stablecoin, you're going to create a new UTXO in the same place, and it's going to be like a massive amount of always for collateral validators and minting policies in there. So what we are going to do in our test scenario, in our example of stablecoin, we're going to attach the collateral validator to some UTXOs that are owned by the stablecoin developer. So we're going to send this collateral validator, the actual validator, to a UTXO sitting at the stablecoins developer address. And we're going to do the same with the minting policy. Now, after doing this, we're going to call this deploying, quote unquote, deploying the validators, but we're actually just like building them and just send them to UTXOs and not really using them, just like putting them in the blockchain for them to be used later. And then there's a feature that is called reference scripts that allows us to, instead of consuming, instead of only being able to run the validator that needs to unlock a UTXO on that is sitting on that specific validator. We can tell in the transaction, we can say, hey, I want this transaction to use as a reference these two validators. So now I'm not consuming the UTXOs of something that is on the collateral validator or in the minting policy, but I'm asking them, I want to create a transaction that can only be approved, that I can only change the array of UTXOs in the blockchain if this validator or both validators return true. I'm not unlocking something sitting on these validators specifically, but I'm saying, not necessarily, but I'm saying, hey, I want this to return true. I don't care. You don't need to know why. I just want this to return true. And then, so that's why we are deploying, quote unquote, these scripts. That means that we're going to pay some fees. The developer, the stablecoin developer, is going to pay significant fees, and it's really expensive to put the contracts there. But from now on, all transactions that use these specific validators don't need to upload the validator again and again and again and again. They can just say, hey, you know that validator that is sitting on that UTXO? So I want to use that one. And the transaction doesn't need to provide the validator itself. Make sense so far? So we are going to reference the script. And another thing that we have to do is being able to update the Oracle, of course. We already saw this in the last lesson, but the stablecoin developer is going to create an update Oracle transaction that consumes the old Oracle with the NFT and creates a new Oracle with the new value and the same NFT. We already saw this, so let's keep going to the interesting part. So, minting stablecoins. Let's see if I can zoom out a bit. Yeah. So this is the transaction that we have to run to mint the stablecoins. What do we have to do? Well, user one has in its wallet a certain amount of ADA that it chooses for it to be a collateral. So this mint stablecoins transaction is going to consume the user's one ADA. They're going to use this ADA as collateral. Is going to reference the script of the minting policy and is going to reference the input of the Oracle validator. What does it mean that it has its reference input? We just explained reference script, but I didn't say anything about reference input. And reference input means that I'm not asking the transaction, I'm not asking the node to validate that this Oracle, the script of the Oracle returns true or false. I'm asking the node to bring the information of this input of this UTXO to the context of the transaction, so then I can use it in the logic of my other validators. So I'm referencing this Oracle validator input, so I can then get this USD ADA rate from the transaction, so the minting policy can actually use it to make decisions. Specifically in this case, make decision if the user one can actually mint or not the amount of stablecoins that wants to mint. So we are in this specific scenario, we are only consuming a single UTXO, but we are also referencing a script that needs to return true, and we are referencing an input so we can access this datum. With all that in the transaction, the minting policy is going to decide if user one can or cannot mint. And if it can, the user one needs to create in the same transaction, this is all a single transaction, a collateral validator that is going to have in its datum, it's going to create a UTXO sitting at the collateral validator. This is really at the address of the collateral validator, and it has as a value the collateral that the user one wanted to be consumed. And as datum is going to have who is the collateral owner. This is going to be needed for us to do the checks later. And what is the amount of stablecoin that was minted? We also need that to make the checks later. And for that money, for that collateral that the UTXO was, that the user one gave to the collateral validator, the user one is going to get in check as a reward these stable coins that he or she wanted to mint. So what does the minting policy in this case needs to check? Well, the minting policy needs to make sure that this collateral, this UTXO, is created with the correct collateral as a value, is created with the correct datum, as the owner is the same one that is where we consume the money with by, and that the amount of stablecoins that were minted are actually 150 at most. In our example was 150%. So this amount of stablecoins, it's easier like this. The amount of collateral has to be 150% of the value of the amount of stablecoin minted. And to know the value of the amount of stablecoins minted, we need the USD ADA rate. So the minting policy has to check pretty much everything, but the key in this case is this output. This output has to be has to have the correct values and the correct datum for the user to get the stablecoins. Then the minting policy doesn't really care how many stablecoins the user gets. The user could put, for example, 150, the collateral that is valued as 150 US dollars, and it could be just 30 US dollars. So it's not mint. It could be, if it puts 150, it could mint at the most 100, but the user could be someone that doesn't want to deal with the nerves of having someone else liquidating their position if the price drops. So I say, okay, I'm going to go from something more conservative, and I'm going to just mint 30 US dollars. So I have a bigger margin of range to make my decision and to be protected in the case that the price of ADA drops. So the minting policy will only cares about the maximum value. So the user one cannot get more than, in this case, 100 stablecoins, but it could get less than those, no problem at all. So that's the checks for the minting stablecoin. For the minting process, we have no stablecoins, and now all of a sudden we have. Then we have the burning mechanism. In this is pretty simple as well. So both the minting and the burning mechanisms are pretty simple. The liquidation one is a bit more complicated. So what do I need to check? What do I need to know to be able to burn the stablecoin? Well, first of all, the user has to provide the stablecoins. So you have to provide the amount of the correct amount of stablecoins to be able to burn them. And what is the correct amount of stablecoins? Well, it's right here in the collaterals validator. So we're going to consume this collateral. And because we're consuming it, of course, we have access to this information. And here, we're going to check that this amount of stablecoins minted is the same that the amount the user is providing to the transaction for it to be burned. So at the end of the transaction, a certain amount of stablecoins go in, which is the same amount that was locked to they were minted when this collateral was locked, and out there are no stablecoins. So the stablecoins got burned in the transaction, and as an exit, there's only the collateral. Now, to be able to unlock this collateral, we have to provide both the collateral validator that decides if we can unlock this, and we have to provide the actual minting policy. Both, as you can see, are reference scripts, so we are not consuming these UTXOs. We are just consuming the stablecoins and the collateral that was minted. And within the logic of the minting policy, we are going to decide if we are allowed to burn this amount of stablecoins, and within the logic of the collateral validator, we are going to check if we are allowed to unlock this collateral. And there's a bit of overlapping as well, because we have to make sure that if we provide a transaction without one or the other, you cannot unlock this collateral without burning the stablecoins or the other way around. So we provide both validators and reference scripts, the stablecoins, the collateral, and you get back only the collateral. But now this collateral is sitting at users one, specifically users one wallet, because user one, we are burning. So the only user that can burn a stablecoin is the same user that minted those stablecoins. So as you can see, that's why we need to save in the collateral datum not only the amount of stablecoins minted, but also who is the collateral owner. So now we can check if the person burning the stablecoins is also the owner of the collateral, so we can give the collateral back. If we wouldn't be able to check this, we wouldn't know if the person trying to burn the stablecoins and unlock the collateral is the owner or someone else that is trying to liquidate the position. And in that case, we will never allow anyone to burn the stablecoins, because unless the price drops, and then everyone can consume this UTXO, so it's a whole thing. So that's why we have to make sure who is the one unlocking. If it's the same owner, if it's the same one that locked the collateral, they can unlock the collateral independently of how much it's worth, the actual minting policy, the actual mint policy is worth. That's the actual stablecoin, sorry, it's worth. That's why we are not providing, in this case, the Oracle. I'm sure you notice that we're not using the Oracle to burn the stablecoins. That's because we don't care about the price of the stablecoin in the case of burning. The same person that minted is the one that is burning, so it's just going back to the initial state, and there's no change in the algorithm. There's no change, no real change in the price of the stablecoin. So you can just allow the user to get this money back independent of the price of the actual price of the asset that is tracking. This is going to become really important at the end of the lecture when we see what happens if the developer goes rogue. So, and finally, we have the liquidation case. So in the liquidation case, let's see if it fits. This one is the most complicated. Yes, like this. This one is the actual, the most complicated one. So same as before, we provide the collateral validator and the minting policy as reference scripts. This is just so we have the actual validators for them to be run. So no need to take much account into that. But it's important that user 2 is providing some stablecoins, but the collateral, it's owned by user 1. Now it's interesting. So user 2 wants to liquidate the collateral of user 1. And the only way that we know that the user 2 is allowed to do that is if the collateral drop the price, the value so much that is below the threshold that we said that we're going to protect the user that locks the collateral. So how do we know if the value dropped? Well, we need the actual amount of USD ADA rate, so we can calculate the current value of the stablecoin and the current value of the collateral locked. And if those values, if the relationship between the value of the collateral and the value of the stablecoin is above the threshold, we are going to reject the transaction. If it's below the threshold, that means the value of the collateral dropped below what we said that we're going to protect the user, the threshold that we're going to say, okay, here is the amount that you can put and the minimum amount you can put, so no one can liquidate your position. And if that's the case, if the collateral, the relationship between the collateral and the stablecoin minted dropped so far that it's below the threshold, then the minting policy and the collateral validator are going to allow the user to burn his or her stablecoins in exchange of user's 1 collateral, which is more valuable for user 2. It's the collateral of user 1 is more valuable than the stablecoins that it's burning. So now, at the end of this whole thing, users 2 is going to own users 1 collateral. So user 2 is going to be that amount richer. And that's the whole thing. So it's compared to everything we saw so far, it's significantly more complex. The actual validators are not like really like way more complex, are just longer, but then with more checks. But the hard part, I think, will be to understand the actual mechanism that we're trying to use to maintain the peg. But after that, the checks that we're going to do with the validators, I just saw them like check that it's signed by the correct person, check that the input has the structure. We already did that with the Oracle, check that the output has the correct structure and the correct values. The checks themselves are not that hard. So yes, a final comment is what this algorithm specifically has the really nice advantage that the person that controls the Oracle, for example, can the Oracle could like shut down or can be deleted or whatever. And if in that case, if we will have to use the Oracle for everything, we couldn't run there will be no way for us to get our money back. Like we mint and then the Oracle disappears and then we have no way to get our money back. But because we specifically made the burn stablecoin in a way that it doesn't use the Oracle, that means that if the Oracle all of a sudden disappears, we could still burn our stablecoins and get our money back. So we are not at the mercy of the owners of the Oracle. All we need to do is to make sure that these two scripts, the always false the collateral validator and the minting policy, are sitting in a place that cannot be consumed. And that's it. And we can be sure that no matter what, if the Oracle, which is the only thing that has to be continuously consumed and created by someone else, if that Oracle disappears, we can still burn the stablecoins and get our money back. And that's it. That's the whole algorithm. It's a bit more complex than what we saw now, I know, but it's also way more interesting than what we saw now. So it's like a real. It's not just if in case I forget to say it later. This algorithm specifically and the way that we implemented the algorithm specifically should not be used in production because there are a few details and vulnerabilities and things that should be changed, polished, or improved before using an algorithm like this one. So as it is, this algorithm is not enough to have a final, like an actual stablecoin, but it gets you a huge boost if you really want to at least get started developing a stablecoin. Understanding how this works gives you at least some sort of initial reference implementation that you can see that you can use to imagine a better and more complete algorithm. So, any questions so far? We're done with this part. Now, from now on, is like the actual example and then looking at the code. Any questions about the algorithm, how it works? Any specific scenario that you want to talk? No? Okay. So now I think it will be cool to see an example, but it's going to take a bit to go through the example, maybe like 45 minutes. And so maybe we should take a break now, like 5-10 minutes. 10 minutes is fine if you think it's okay, Lars.
Yeah, that's okay.
Yeah. Okay, so see you everyone at 22 or sort of 20 something.
Yeah, okay.
Okay.
See
Okay.
you.
Okay, should we continue?
Yes.
Awesome. Perfect. So let's actually use our stablecoin. So to use it, I'm going to go to the off-chain lesson 7 frontend. And I'm going to run, this is a Next.js application. That's the front-end, not part of the blockchain. So npm install to get all the libraries. There you go. And npm run dev. Okay, so we have this localhost 3000. And actually copy, I think I'm going to create teaching recording session. And open it. No, this is not it. This is the key. Well, it's 3000. I can just type it out. Whoop. Oh, I canceled it if I wanted to. Okay, so let's refresh. There you go. So that's our stablecoin. That's the front end that we're going to use. Let's zoom in. That's enough? Too much? Okay. So we're going to do the whole process. We're going to act as the oracle. We're going to act as the owner of the stablecoin, and then we're going to act as the user of the stablecoins. We added the oracle to the front end so we can easily update the price of the oracle without changing backend code and stuff. So it's nicer to see. So, and I prepared, wow, super slow. And I prepared a couple of wallets, Oracle owner, and we have the Oracle owner, we have stablecoin owner, we have stablecoin user 1 and stablecoin user 2. So now we are the Oracle owner. And as we said at the beginning, we need to actually deploy the Oracle so the other, let's see if I have the correct wallet. KDP, yeah. So it's running super slow for some reason. So we need to deploy the Oracle. And as we said before, here in the information table, we're going to have all the information that is going to be queried from the blockchain mainly. For now, we need to mint the Oracle NFT. And as you can see, the Oracle owner is getting 1 asset. And if we get, wow, this is super slow. If we get the asset, we see that the oracles, it's an NFT. There's 1 NFT. Okay. Sign. No, it was. So we sign the transaction, we submitted the transaction, and now we have to wait. Oh, it's already there. So as you can see, the mint oracle button now is deactivated and the deploy oracle was activated. And if we check our wallet, super slow. But if we check our wallet, we see that now we have the oracle's NFT. So let's use this NFT to deploy the oracle. I don't know if I should like close the Docker so it can go faster. Yeah, yes, I'm going to do that, I think. Let's send the Oracle is going to send the NFT to some other wallet. Yeah, I don't know why. I'm guessing it's because I'm running inside the Docker container. So just in case, I'm going to remove that. And I'm going to run it here, cd into off-chain, lesson 7, front end. Was it like this? So now, again, I'm the front end and npm install. npm run dev. And now let's start over. Let's see if that helps with the speed. Okay, so we are back again in the same scenario. We are the Oracle owner and we mint an NFT. Sign the and now we have to wait for a bit. So, oh, it's already there. Amazing, super fast now. So let's deploy the Oracle. Let's deploy the Oracle. Let's start again. I don't know what. Let's see. Okay. So maybe I did it too fast, and now I was trying to consume the same UTXO I was consuming the previous transaction. Okay, so let's start over. Let's mint an Oracle's NFT and plus the Oracle NFT, sign the chain wallet. Let's make the chain wallet password. Okay, so we have the transaction. Awesome. And now we wait for a bit. Okay, it seems that everything is okay now. So we have to wait for a bit for the actual preview blockchain to validate the transaction and give us back the Oracle's NFT. Awesome. Now we can deploy the Oracle. And as you can see, we lose the Oracle's NFT asset because we are paying that NFT to this contract address. Sign. Okay, so we submit the transaction. If we take a look at the right, here we're going to have, when the front end updates, the UTXO where the NFT is currently sitting in the Oracle, of course, and the actual datum in the Oracle. They should be 100. So if the front end works correctly, we should get here an 100. And we have to wait for the transaction to actually be processed and added to the blockchain. If anyone has any questions. There you go. Awesome. So now we found that there is an Oracle with the NFT in the Oracle's address, and that the datum of the Oracle is 100. And if we actually go there, we could go to the transaction detail that actually deployed the Oracle. we see, let's zoom in a bit. Okay, we see here that this is our the wallet's address that we send the NFT that now is in the Oracle's address. And if we see here, it says inline datum. And if we go to the inline datum, we see that it's 100. So this is the current USD, the current ADA price in US dollars. Awesome. So we have our Oracle up and running. Now we need to deploy the scripts. So let's change to the stablecoin owner wallet. Refresh this. And now we hit on the deploy scripts. We're going to see what this means when we take a look at the contracts. But this just like in practice, we are applying some parameters to the minting policy, and then we are creating UTXOs that have one has the collateral validator attached, and another one has the stablecoin, the minting policy, stablecoins minting policy attached, and both are going to be sitting at the stablecoins owner address in this example. So then, like, you can do this as many times as you want to practice or to understand better how it works. And every time it's going to deploy new validators and consume the old ones. So you're not going to like accumulate validators anywhere. So let's sign the transaction. Okay. And now we have here to the right, we have the transaction that deployed the reference scripts. We have the stablecoin policy ID in hex and the asset class, which we said that was the policy ID plus the token name in hex as well. And we don't have the minimum percent unlocked, but we don't have it right here, but we know that it is 150%. So this is the threshold that we chose. So because, like, just to make our examples simple, we chose that you have to lock 150% of value in the collateral of respect. So you have to lock 150% of value more than the amount of you mint. So you are getting 100% and locking 150%. So there's 50% extra of value in the shape of ADA locked in the collateral. So this is our threshold. Okay, so the scripts are likely already deployed. So what we're going to do is we're going to move to the user. I'm not sure why, but this is struggling a lot. So I'm going to change to the point of view of the user 1, in this case, stablecoin user 1. And I already minted in another occasion. So let's just send these ones so they don't bother us to some other wallet. It was 20, right? Send. Okay, so now we have to wait a bit for the stablecoins to go away. And I'm going to like send them because these were parameterized using different parameters. So if I just keep those and mint more, we're going to have 2 coins with the same name, but actually different policy ID, and it will be super confusing. So I'm just going to send them away and start from scratch. Now let's update the front end. F17. Yes. Now we have to wait for this transaction to go away. But in the meantime, here from the user perspective, we need to use both the collateral, we need to use the collateral validator and the minting policy validators. And we don't have those as user because the stablecoin owner deployed them into the blockchain. So now the user, not like really the user, but the front-end developer that builds the front-end for your stablecoin, needs to use, it needs to reference those UTXOs. So because every time that I run this example, there's a new reference, I just added these two fields. So now we have to add the UTXO reference for the collateral and minting policy. So what we're going to go is we're going to go to the transaction that deployed the reference scripts. And here in this transaction, we see that the owner of the stablecoin consumed just ADA, his own money, and sent back to his wallet, because as you can see, 8QY3P, that's everything is back in the user, in the developer and the stablecoin developer wallet. We have not only just ADA, but also we have two outputs that they have inline datums and reference script attached to them. So this is the UTXO that has one of the validators, and this is the UTXO that has the other one, the other validator. If you deploy them, you will know which is which, of course. But it's really easy to spot that there's one validator that is significantly larger than the other one. One to lock the one validator, we had to put 6.67 ADA to pay for the place in that UTXO, for the UTXO to hold our validator. And this amount that we pay to hold our validator depends on the size of our script. So there's a script that is relatively small, and then there's another that is like three times bigger. And this one is actually the minting policy. So the minting policy is significantly bigger and more complex than the collateral validator. So I know that this script right here, if I click, I know that this script right here is the collateral validator, and this script that is attached to this UTXO is the minting validator. So what I'm going to do is going to go to the transaction to get the UTXOs. Let's go to the UTXOs. And the transaction started with F979, so we have one. That's not right. Oh, okay, so we have two pages. So we have this F9 transaction. These are all previous transactions from the previous UTXOs generated by previous transactions by the same person. But the transaction that we, in this case, used to deploy the stablecoin was the one that started with F9. So we have one output of this transaction that is like 5 ADA locked as an amount, and we have here an actual script in this validator. And if we go to the other two that are of the same transaction, we have 17.6 ADA with the other script that is of index 1 and the change Like this has no script attached, has no datum. It's just money, like without anything else. So this is a transaction that we're going to use as part of our reference, and then the other part of the reference is the index. So the minting policy has index 1, and the collateral has index 0. So if we go here, we paste the transaction, and we use this hash tag, this pound sign. I don't know how, depending on how old are you, you say this differently. So we have the numeral there, and if collateral was index 0 and the minting policy was index 1. Okay, so those are the reference to the UTXOs that contain the minting policy. So from now on, we can use the same ones because we are using as a reference. We're not consuming that, so they're not going to change. We're going to use those to generate to mint, burn, and liquidate our stablecoin. So what do we want to do? Well, first we want to get the actual UTXOs. We have only the reference here. So let's click here, get the reference scripts. And if we did things the right way, okay, we found the actual UTXOs in these addresses. So we were correct. And now I want to double check that I'm user 1. Yes, I'm user 1 and it's in 7F7. Perfect. So I'm user 1 right now. And user 1 wants to mint certain amount of stablecoins. And if I want to mint 10 stablecoins, I have to lock 15 ADA because currently the price of ADA in USD cents is 100. So 1 ADA is $1. And because I need to lock 150%, this value has to be 150% the value minted here. And because it's 1-to-1, we can just say 15 USDA, I call them for this lesson, USDA, to get 10 stable coins, 10 USDA in our wallet, we need to lock the value of 15 USDA. So let's do that. Let's mint our first stable coins. Let's just click mint. And as you can see, we are paying 15 ADA to get 10 USDA. Sign. And now we have to wait for a bit. Let's go to our wallet. So now we should get our newly minted stablecoins in our wallet. And after that, we can just start using them like anything else. So I can send this, I can use them to buy something in a marketplace. I can do whatever I want. They are just a native token like everything else. So like I don't need to interact with the contracts unless I want to either mint more, burn them, or liquidate someone else's position. So the usage of the stablecoin is not dependent on the actual smart contracts, as we said in the prior lesson. So we have our 10 newly minted USDAs. First test that we want to run is to see if we can burn them. So we could mint them. Awesome. It works. We have them. Now we want to check if we can burn them, right? Because for some reason, I want to get my money back. So we need to provide, to be able to unlock the collateral, we need to provide the actual collateral that we want to unlock. So if we go to the transaction that we used, actually, if I click here and I go to this history of transactions. And I click in the actual transaction. I have the actual transaction they used to mint. So I just pay, I just like consume this UTXO and output 15 ADA for the Oracle, 15 ADA for the collateral validator, and 10 stablecoins USDAs for my own wallet. And of course, there's a minimum amount of ADA that needs to be part of every output. So in this case, it's just one ADA, 1.14 ADA. But the important part is that now we have our stablecoins. And if we explore a bit this collateral UTXO, there are a bunch because I already used this previously. But if you take a look, this F8 was the transaction that I just did. Index 0, and I locked 15 million Lovelaces, so 15 ADA. And if I take a look at the datum, this is the collaterals datum, we see that it's encoded now in bytes, but we see that we have 3 fields, and we know that these fields indicate the stablecoin's owner, the stablecoin's minting policy ID, and the amount of stablecoins that we minted by locking this UTXO, by locking this collateral amount. So now what we want to do is to unlock it. So if I go back, we have this F8. I need, again, to get the reference. In this case, the reference of what I just created. So index 0, F8, I think it was F8. If I go back, yes, F8. So let's put the reference to the collateral that we want to consume. Right here. Right. No. This is not working. There we go. So we have the collateral that we want to unlock. Now we have to say how many stablecoins we want to burn or liquidate, because depending on if this collateral is ours or not, we should burn or liquidate. In our case, we want to get back to the initial state, so we make sure that we could mint. Yes, we can. We now want to make sure that we can burn, and then we want to try liquidating someone else's position. So now let's see if we are actually user 1 and we have 10 USDA. That is exactly the amount that we just saw here in line datum. We need to burn 10, so we have to provide here 10. And let's get the actual UTXO of the collateral, and let's burn the stablecoins. There you go. And if we see right here, we see that we gain 14.8, so it's the same 15 that we locked minus the fees, and we lose an asset, and this asset is 10 USDA. Sign. And now if we wait for a bit, we should lose this 10 USDA and get almost 15 ADA back. So we are 2 out of 3 cases that worked. If you have any questions, please let me know. Wow, this is taking a lot of time, so let's see. Minus 15 ADA, yes, this is the old one. So while we wait, let's go step by step first, just in case. But now we want to liquidate. So what are we going to do like after this transaction passes? What are we going to do? So the first thing that we need to do is someone has to create has to like mint stablecoins. Then we are going to update the value of the oracle. So so now, like after the value of ADA drops drops significantly, the threshold, the amount of ADA locked in the UTXO we just created, in the collateral we just created, is below the threshold. And then we're going to play the role of a second stablecoin user that is going to mint a correctly over-collateralized stablecoin to be able to, in part, burn the user's one, to not burn, liquidate user's one position to get the extra money to himself. Why? Let's see, I have the transaction right here. Okay, so the transaction passed 21 seconds ago. And as you can see, it consumed the collateral, it consumed the stablecoins, and it gave back just ADA to the address, to the correct address, which is the same in this case that the owner of the collateral. So it was 21 seconds ago, so it should be here, right? Yes, awesome. Okay, so this collateral doesn't exist anymore because this we did consume. But now user one, because user one never learns, is going to mint again the same amount of stablecoins. We're going to mint 10. Sign. Okay. And well, eventually it's going to go, but we can keep going. So the user one minted stablecoins using the current value of the oracle, which was 100. $1 is 1 ADA. But then something catastrophic happens, and now ADA is worth 90. Whoa, sorry. Let's try it again. Now, ADA is going to be worth 90 US cents. So 1 ADA is going to be $0.9. So that means that because user one minted exactly like the maximum amount possible of stable coins, it's right above the threshold. So as soon as I update this oracle, then anyone with stable coins is going to be able to liquidate users one's position. So I'm going to change. So stablecoin user one already got the stablecoins, but now I'm playing the part of the Oracle. So there we go. If I don't change, it's just going to reject the transaction. So let's update the Oracle. As you can see right here, it's 100, but after this new transaction gets added to the blockchain, this 100 is going to become 90, which is 90 cents, the value of an ADA. There you go. If we go there, we see that in this transaction, we consumed a UTXO in the Oracle's address that has the Oracle's NFT with the value of 100. And we generated a new one in the same address with the NFT with a value of 90 and a bunch of stuff that we didn't generate that. Those are prior transactions. So the Oracle updated, and now user 2 has the incentive of minting stablecoins correctly collateralized. User 2 already has stablecoins. Oh. So I'm going to get rid of the old USDA stablecoins, and I'm going to mint new ones with the correct policy ID. And, well, right. Well, so user 1, there you go. No, it still has it, but let's keep going. So let's go to user 1, and let's see the transaction that gave us the USDA. So let's go to this transaction. So this transaction 3 minutes ago was the one that user 1 created to lock his 15 ADA and mint 10 USDA. And now we want, because it's below the threshold, we can liquidate him. So we are going to get the output reference of this output. So the one that actually has the locked value. So it's 53.9. And if we go to UTXOs, these are all the UTXOs here. And one of them is the UTXO created by this specific user, 53.9E. So this is the transaction and index 0. So this is what we want to consume. No, index was 0. And if we get the collateral UTXO, okay, found the collateral, amazing. So we found users 1 collateral for his stablecoins, but we are user 2. And user 2 forgot to mint the stablecoin. So user 2 is going to mint, for example, it's going to mint 30, maybe 30 stablecoins. And the minimum amount of ADA that needs to put It's not actually 45, it's a bit less, but this was calculated automatically. So this is a bit over the threshold. But this user 2 is smarter than user 1 and decides to collateralize even more. So instead of 45, he's going to put, let's do 60. Let's do 60. So 200% of the value, roughly 200% of the value, is going to be minted. So if it keeps dropping even a bit more, this user 2 is going to be still protected. But this user 2 is really interested in getting users 1's money. So let's mint. We are user 2 right now, and we are giving 60 to mint 30. And now that we have our correctly collateralized stablecoins, eventually we'll have our correctly collateralized stablecoins. We will be able to liquidate users 1 stablecoins that are under collateralized, and they are over collateralized, but just not enough that it surpasses our threshold. Okay, so we have our 30 ADA, user 2, and now we chose to liquidate users 1 position. If we get the collateral, I think we already did. And we shouldn't be able to do this unless user 1's collateral is below the threshold. So if we can, that means that it's below the threshold. So we are paying 10, the value, we are paying back the value of 10, roughly like $9, and we're getting back $10, sorry, and we get back the value roughly of like $14. So we're gaining around $4 just to liquidate someone else's position. So let's sign. And now we wait. And user 2 now has 30, but eventually we'll have just 20, but it's going to be richer. And it's going to help us. It's going to play his part, his role in maintaining the peg. So we tested all happy paths, all scenarios that were correct. Like we didn't try to burn being a different user. We didn't try to liquidate someone position if we couldn't. We didn't try to mint more stable coins than the amount of the collateral, but all those cases will just fail. And you don't need to trust me. You can just do it yourself. You can just try all combinations and you will see that they are going to fail. But here we don't have enough time to try everything. So we just went through the happy path. There you go. So we have now only 20 USDAs, but we are around $4 richer. There you go, 14. And that's it for the demonstration of how it uses. I hope that between the overview and the algorithm explanation with the diagrams and the actual usage of it, it makes sense. Now, after this, we're going to go through the code. Okay, so let's see. We have any questions about anything we talked so far? No questions? Everyone is understood perfectly? Okay. So, awesome. Anderson understood for sure. We are going to cover the collateral, which is pretty simple, the collateral validator, which is pretty simple. And then we're going to have a break before the minting one, because we just had a break. Or should we do it right now? No, it's not so long. Right. So I don't have to like use the same exact version of Aiken as in the, where was it? Oh yeah, here. So validators, lesson 7. So we have, I hope it's fine that I'm not going to compile the validators with the same exact version, so I don't need to use the Docker image. It's slowing down my computer, so I'm going to avoid it. So we have 4 validators. We have a collateral validator, we have a minting validator, we have an NFT validator, and an Oracle validator. We are not going to talk about the NFT and the Oracle one, mainly because they are exactly the same as we cover in the minting lesson and Oracle lesson. So you already know how they work. You already went through every line of the code because we wrote every single line one by one in this course. So we already know that. We're just going to cover the collateral and minting validators. Just so I have access to everything, I'm going to open the whole folder. And if we go to validators, lesson 7, let's talk about the collateral. So let's see minting scripts nodes for more information. Minting. So here I have some extra information. Let's see what I wrote here. This script contains the bulk of the checks. So the bulk of the checks are in the minting policy, both for also like for minting, burning, and liquidating. You can use it by itself because there are some checks that need to be made on the collateral script. So the minting policy is not enough. The collateral also have to like make some checks. And the algorithm is super simple and something you should understand in the implementation. This means that it's a great introduction to the topic, but it has flaws. This is what I said at the beginning that had make it unsuitable for real world application. We will talk about them after going through all this. And about the implementation, the script is divided in 3 parts: mint, burn, and liquidating. Each part has its own checks, although some logic is shared. The script is optimized by readability and simplicity, so it's not the most efficient one. But we're going to talk about how to optimize it if we make in time. But we're going to start with the collateral one because the collateral is like the simplest one. So collateral validator, instead of like writing everything from scratch as we did until now, just for the lack of time, we're not going to do that. So the collateral validator has 2 possible states. Either it could be redeeming or liquidating. Why not creating? Well, same as before, like when we are creating a UTXO, we are not running in a validator address, we are not running the validator. So the checks that we have to make sure that is being correctly created have to be part of the minting policy. So the collateral redeemer, the collateral validator only cares about either burning, redeeming. The redeeming is used when the same user that minting wants to burn, or liquidating. This means that when some other users tries to liquidate a user's position. So these are the two scenarios. And if we go to the collateral, we see that there's no parameters. So the validator has no parameters, which is, I think, the only validator in the whole, the only validator except for the, no, yeah, this is the only validator that has no parameters. All parameters are going to be part of the minting policy. And it's just a single collateral function that has the collateral datum, the collateral redeemer, and the script context. The collateral redeemer we just saw, the script context we already know, and the collateral datum, we don't have code to definition in Aiken yet, but hopefully we will soon enough. But collateral datum comes from stablecoin shared. So shared. So if we go to collateral datum, it's right here. I think if I do, there you go. So what is highlighted is the important part. So the collateral datum has 3 fields inside: the collateral minting policy ID, the collateral owner, and the collateral stablecoin amount. We need to know for the algorithm itself who is the owner, which we provide the Punky hash, and we need to know the amount of stablecoins that was minted used locking this collateral because of the algorithm. But on top of that, because of the implementation, we have to provide also the minting policy ID that this collateral datum is locking to indicate for which tokens this collateral datum locked from. So if we have more than one minting policy, we could, in theory, provide different policies IDs, but use the same collateral validator. So if we go back, so we have our collateral datum that has all those 3 values that we just saw, the redeemer and this context. And we return, as always, a Boolean. We start with the purpose when the context is spent. And as always, if it's not spent, we just return false. So we only care about spending validators. We don't care about minting. We don't care about anything else. So only spending validators. So if we spend, we get the amount of tokens minted in this specific transaction using this get total minted stablecoin that I define in the shared directory. So I created a library. Let me show you. I created a library in examples Aiken called stablecoin shared, and I put like some types and some functions that I want to share between validators. So I'm going to use this get total mint stablecoin to get the amount of stablecoins mint in the transaction as an integer. So then I can compare. I can do inequality operations. So I provide the context and I provide the policy ID of the stablecoin. And all I do is I get the mint value from the transaction. We already saw it a bunch of times, like what the mint value is and how you have to go from mint value to a regular value. And then once you have a regular value, you have a bunch of functions. So in this case, we have the mint value, and from the mint value, we extract the abstract. We take this mint value abstract type and we convert it into value, regular value. And once we have a regular value, we use this quantity. We use this quantity function, quantity of function that gives us exactly what we want, a number saying the amount of tokens of a specific policy ID and token name in this value. So for that, we need to provide the policy ID that we provide as a parameter and the stablecoin token name that we conveniently define in the share stablecoins, because we have to use this hard-coded value. We have to use it twice, once for the minting and once for the collateral validators. So we just put it there. And actually, that was the initial idea, but then I realized that I can just extract this function to the shared library. And because this token name is only used by this function, I don't need to actually like use this anywhere else. This is just defined privately here for this function to use it, and then I'm just making public this function. So that's nice, I think. And so we have by running this function, we have the total mint stablecoin. So once we have this number, we have to check that here, we have to check that the stablecoin amount is correct. What does it mean? What does it mean that it's correct? It means that the transaction creates the transaction mints stablecoins and also creates, like as the Oracle datum. Sorry, let's go back. It doesn't mint this, as we said before. The Oracle, the collateral only runs when we are burning or liquidating, not when we are minting. So in this case, when we check the stablecoin amount, we know that because we are either burning or liquidating, both cases at the ledger level are burning stablecoin. So they are making a stablecoin disappear. So the minted value, it should be a negative value. And because we have in this datum a positive value in this datum, in the collateral datum that we have right here in the collateral datum, we have the collateral stablecoin amount that is an integer, and this was created positive because it was created when we minted the transaction. So we know that this integer should be positive, and that's why here we say, okay, the stablecoin minted amount should be equal to the collateral stablecoin amount. We know that the stablecoin minted is negative because we are burning. So we take the collateral stablecoin amount from the datum and we just change its sign. So we make it negative. So what does it mean? It means that the opposite sign, like the negative value of the stablecoins that were amount, should be exactly equal than the stablecoins that are actually being minted in this transaction. So if the datum says 30, we should check that minus 30 is equal to the stablecoins that we are burning. So minus the datum, the stablecoin datum should be the same as the stablecoin actually being burned. Here it says stablecoin minted, but minted, a negative mint value means burn. I think we already discussed this in the NFT lesson. So that's what we are checking. We are checking that we are burning the same amount that was previously minted. So, and this check works for both when the redeemer is liquidate and when we are redeemer. So in both cases, when someone else is trying to liquidate the position, and when the same person that minted wants to get his money back, in both cases, we need to do these checks. When now that's why these are like outside the redeemer clause, because when the redeemer it uses this check. So when the redeemer is liquidate, that means that we are liquidating someone else's position. And that means that the collateral has to make sure that we are burning the same amount that was originally minted. There are way more checks that we need to do, but all the other checks are part of the minting policy that runs at the same time. And how can we be sure that it's running at the same time? Well, because we are checking that this specific stablecoin is being burned. The only way to burn a stablecoin is by running the minting policy that is able to mint and burn. So this check not only checks that the correct amount is being, the correct amount of stablecoin is being burned, but also checks that the actual minting policy is being run as a validator, and that we need that minting policy needs to return true for it to validate. So this check is going to work in conjunction with the minting validator, with the minting policies checks. And then the other case is the redeem case. So in the redeem case, we are burning our own stablecoin. So we have to check that the stablecoin amount is being burned is the same that it was minted before. But we also need to check that the person that signed the transaction is the actual collateral owner, because the only person that can redeem is the owner. So in the collateral case, there are more checks in the collateral validator, but in the minting policy case that we're going to see after the break, the liquidate has way more checks because there's a lot of maths being involved. But the redeem case has virtually no checks because these are pretty much anything that we want. We want to make sure that the stablecoins are being correctly burned and that the owner is the one that is getting the money back, and that's it. And that's the whole thing. That's there you go. So that's the whole validator. It's really small, actually. Let's see if I can. That's it. That's the whole validator. It's not big. And it has a bunch of like explanations, documentations and stuff. So any questions about about the logic implemented in this particular validator? Or anything?
No, in the chat.
Not in the chat. Thank you, Karina. Any other questions related about stablecoins or the algorithm or whatever? No? Okay. So we end at 4. So let's take just 5 minutes because I don't want to run out of time. If it's fine with everyone, I wouldn't take any breaks, but I realize that people need to go to the bathroom and stuff. So let's take a 5 minutes break. Do you think?
Okay, yes.
Okay.
Yes.
Okay. Okay. See you everyone in 5. Okay, so should we continue?
Yes.
Thank you. So let's finish this. Last validator that we need to take a look at is the minting policy validator. So this is the most complex one. And if you saw the Plutus TX one, it's going to look a bit different because Aiken has different restrictions. So else, don't worry, it's not that. It's just long, not significantly complicated. So important, really, really, really important part is that we have parameters. We have many minting parameters. These parameters are there to make sure that once we create the final stablecoin policy ID, you cannot change the threshold, like no one can change the threshold, no one can change the logic of the collateral validator, and no one can change which oracle we use. So this is a way to prevent tampering, basically. In our case, we provide the oracle validator script hash, we provide the collateral validator script hash, and we provide the minimum percent an integer, which is this 150 that we saw in the UI. This is the minimum percent of collateral log. So in the example, we said that we wanted to log 150% of the value minted. So in that case, it will be 150. We're going to use this to make some calculations to calculate the maximum amount of minting of stablecoins that you can mint. Then the minting redeemer has, in this case, has 3 cases. So this case is different that the collateral that has only 2 cases for the burning and the liquidating. The minting redeemer has also the minting case, the minting possibility usage. And that's because we actually need it. We need to logic to decide on the minting policy. And so when we actually write the validators for the minting case, those are the only checks that we do to make sure that we are minting. When we are running with the burning, we are sharing some checks with the collateral validator that we just saw, and when we are liquidating as well. We will see maybe one after the other, like side by side to see, but for now, let's focus on the minting params, on the minting stablecoin. So we have a single validator. This validator takes the minting parameter we just saw, and it creates a single function, the mint stablecoin function. It's a minting policy, so it only takes a redeemer, and of course, the script context. The minting redeemer can be either minting, burning, or liquidating. And then we start with the checks. First thing we do, as always, we check that we're actually minting. And not only we expect that this is a minting policy, but we actually use this check to bind the actual policy ID of this validator to a variable that we call policy ID for later usage. Another thing that we're going to do is we're going to extract all the values of the script context that we're going to use. So in our case, we're going to use the transaction of the script context. And inside the transaction, we're going to use specifically only the inputs, outputs, reference inputs, and the extra signatories. So we do all this upfront because the structure in Aiken is expensive, so it's better to do it just only once. So we have now, we bind the inputs, outputs, reference inputs, as extra signatories. It's important that we already have that. We don't need to do context.transaction.whatever. So when the redeemer is minting, the first thing we need to check for mint is the oracle rate. What is the rate, the current rate indicated by the oracle? For that, we extracted this get oracle rate. Now we have, go to definition, we have this get oracle rate function that takes a list of reference inputs. We are not consuming this one. We are just reading the information in these reference inputs. And the script hash of the oracle validator. Once we have all the reference inputs and the hash of the oracle validator, we can filter all the inputs, all the reference inputs to see, to get only the ones that are actually in the oracle validator's address. So that's what we do. We already did something like this for the actual implementation of the oracle. So nothing new here. We take all reference inputs and we filter them using this anonymous function. And this function says, okay, so for each okay, for each input, we get the output. From the output, we get the address. From the address, we get the payment credential. We saw this 2 days ago, so I'm sure you remember. Then once we get the payment credential, we have 2 different options for payment credential. It could be either a script or a wallet. So if in the case that it's not a script, we just return false because we don't care about maintaining this oracle input, this reference input. And if it is a script credential, we bind the actual hash of the script and we compare the script hash with the oracle validator hash. Maybe this should be called oracle val hash, but well. So this oracle validator, this check is going to filter for every reference input. If it's not a script, drop it. And if it is a script, only keep the scripts that are actually the same as the oracle validator. So we should get, if we know that the oracle has just one we are providing just one oracle reference script because there should be only one, because it contains an NFT and there are no 2 different NFTs. So there's only one oracle validator. So after this whole filtering thing, we get back a list, and we know that this list should contain only a single oracle input. So we pattern match the list for a single value called oracle input. And now we bind the oracle input value. If there's more than one, or if there's none, this is just going to fail. So if we try to run the minting policy to mint stablecoins and we cannot find the oracle input, we're just going to fail. You have to provide the oracle to be able to mint. Once we have the oracle's input, we can take the rate from it. So how are we getting the rate? So we get the datum, oracle inputs, as all inputs have outputs. So the actual output that contains everything about this output, between all these, the things that it contains, the value, the address, etc., has the datum. So we can access the datum of this oracle rate, the datum of this oracle input. And when we try to access the datum, we know from last lesson that we have 3 options. We can either have no datum, we can either have no datum, datum hash only, or inline datum. In the previous lesson, we said if we have no datum, we just return false. In our case, we are going to fail with a nice message that it says, hey, I couldn't find the oracle's datum. So in the case that it fails, at least it tells us why. If if we find a datum, but it's a datum hash, in that case, we are just going to say, we're just going to fail. Like we could do something else, but in this case, we're just going to fail because the datum should be inlined for other people to find, to be able to read your datum and be able to liquidate your position. So we're forcing, by doing this check, by failing this, we're forcing you to provide the actual datum inline instead of just the hash. So we fail if the datum is not inlined. And in the case that the datum is inlined, we return the datum. This datum, we saw 2 days ago, that this datum is of type data. But we also saw 2 days ago that we can use this trick, not a trick, but an actual feature of the language, that we can expect that a certain value of type data has a specific shape. In this case, we say that we expect that this data is actually a string. And if you cannot parse this data into a string, an int, if you cannot parse this data into an int, just fail. By doing this expect, we make sure that not only there is an inland datum, but that the datum is actually a number that we can use in our algorithm. And if that checks out, we return the oracle's rate right here. So this whole thing was to get the oracle rate into our minting policy. Now that we have the actual oracle rate, we need the collateral's outputs to be able to do the checks. So now we are going to use this really handy function, find script outputs function. And we're going to provide the outputs. And this find script function, I define myself right here. So this find script outputs is going to take a list of outputs and a script hash, and is going to filter. Same mechanism as before. We provide all the outputs and then we filter him with this anonymous function that takes each output and address, payment credential with pattern match. If script credential is an address, and if the script is if the credential is an actual script, we check that this script is the one that we are looking for. So we are finding all the outputs that are sitting at this specific script. And if it's not, if it's a wallet, we just return false. So after this filtering, we get only the outputs that are actually sitting in this script hash. And that's how we get a list of outputs of, in this case, the collateral validator. We are using the script hash we saved in the parameters. We are passing the collateral validator script hash. So this find script function, this find script outputs function, is going to give us a list of all the outputs of the transaction. Outputs, nor inputs, the outputs. So the outputs that we are creating in this transaction that are going to sit in the collaterals validator. And we know, or we assume, that there should be only one, because we are making a transaction in this implementation. We are choosing so that you can only create one collateral at a time. So we expect that this collateral, this list should contain a single collateral. So we bind the collateral output name to it. And now, once we have the collateral output, we use this get collateral datum function that we also define ourselves to get the datum, which does the same checks we did before. We expect, we do output.datum, and no datum we fail, datum hash we fail, inline datum we return the datum, and then we expect that the output datum should have the collateral datum shape. So we should be able, and we are parsing the datum value to collateral datum. If that's not possible, that means that it doesn't have the proper shape, so we fail. But if it does have the proper shape, that means that we got ourselves the collateral outputs datum. And now we could do all the checks that we really wanted to do from the start, because we have the actual information that we needed. So the first thing that we're going to do is to get the collateral amount. Like we have the output right here. We got the collateral output, and then we got the datum of that collateral output. But we also need the value locked by that collateral output. But we only care about the lovelesses of this value. Values can contain multiple tokens, but the only tokens that we care in our implementation is the ADA, loveless value. So we get from the collateral output value only lovelesses as an integer. So now we have the output amount and we have the datum. And as well, we need the actual total minted stablecoins. This is the same function we used before. So we already went through this function before we used in the collateral. Now we are seeing at the minting policy. And now we have all the information that we need, and we can start doing the actual checks. So first check, we're going to check that we are actually minting and not burning. So because we are in the minting redeemer, so we are going to make sure that the stablecoin minted amount is bigger than 0. That's the first check. Then we want it to be bigger than 0, but we also want it to be less or equal that the maximum that it can mint. So we are going to calculate the maximum minted amount. We're going to provide to this max mint function the collateral output, the amount locked in the collateral output. We're going to provide the oracle rate, and we're going to provide this mint %. And here is the magic. This little thing, which is explained in the comments, like how we arrived to this formula, but this little formula calculates, it's a basic math, calculates the maximum amount of stablecoins that we could mint based on the oracle rate, the mint %, the threshold that we define, and the collateral amount that we are currently locking. So this is just multiplications and divisions, and we get an int back, and this int is the maximum mint amount, and we want to check that this maximum mint has to be bigger or equal than the actual minted amount. Makes sense, right? So we want to make that the stablecoin minted amount is both bigger than 0 and less than the maximum that we can mint. So here we have one Boolean, check mint is positive, another Boolean, check that max mint is correct, check that we are not minting more than we should. And finally, we want to check not only that the actual minting part is correct, but that the output that we are generating has the correct shape. So we're going to check the collateral output datum. We're going to provide the actual collateral output datum. We're going to provide this minted amount. We're going to provide everyone that signed this transaction, and we're going to provide the policy ID of this minting policy that we are running right now. And if we provide that to our function, we have one last helper function that is going to just check with the AND operator. Is we're going to check 3 different Booleans. First Boolean that we need to check is that the collateral output amount, the datum, contains a stablecoin amount, and this stablecoin amount in the datum has to be exactly the same as the amount that we're actually minting. That's the first check. So we created the datum. That datum has a number inside. and that number has to be exactly the same number as the stablecoins that we're actually minting. Then we want to check that the policy ID of the minting policy that we are running right now is the one that we have saved in the collateral. So you cannot mint one stablecoin and save in the collateral for a different stablecoin. And finally, we want to check that the transaction has been signed by the collateral owner that is written in the datum. So in the datum, we said that there's a specific collateral owner, and we are making sure that this transaction is being signed by that specific collateral owner. So you cannot create collateral for someone else. You have to mint for yourself. And that's the last check. And now we have to combine them, combine at least the ones that we didn't expect, that we just used the let binding. So for actually like running the checks, we have to say that, okay, is the check, is the mint positive? What we define right here is check mint positive, check max mint, and check collateral output datum has the correct shape and types, correct shape and values. So those are the three checks that we do right here. So is mint positive? It should. The check is below the maximum? Yes, it should. And is the collateral output datum correctly constructed? It should. If all these pass, that means that we are able to mint. Not only that, but yes, only that. So that's it. But I'm running out of time. So that's the minting part of the minting policy. And these are all the checks that they are needed. We don't need any other checks. The collateral validator doesn't do anything in this case. Everything is like constrained in this redeemer. Then we have the burning case. We're going to sort of repeat a bit, so we're going to skip the things that we already saw, but we're going to do the same thing that we did before, but for the input. Now, before we wanted to create an output on the collateral address, but now we are consuming an output from the collateral address. So now we have a list. We are going to find script outputs inside the inputs of the transaction. So what are we going to do? In this case, this is one way of implementing it, but there's another way that is more efficient, of course, but it's a bit longer. So we're going to first, from all the inputs, we are going to get the outputs, and now we end up with a list of outputs. And then we use the same find script output function that we used before to filter the outputs and to get only the ones for the collateral validator. So now we have a list that should contain exactly one collateral input, and we will get from that collateral input all the information. We parse the collateral input datum, same exact way as we just did. We just use the get collateral datum function, and it fails if it's not there, and if it's a hash, it fails if it doesn't parse to collateral datum. So at the end of the day, if this returns a value, it's the correct value with the correct shape. So we have the collateral input, we have the collateral input datum. We check the owner's signature. We did it like 5 times until now. We just check that the extra signatures has the collateral, his was signed by the person that was saved in the datum of the collateral. The collateral's datum has a person in there, a collateral owner, a pubkey hash that we just check in the minting policy that has to be the person that signed. Well, in this case, we need to check that the person that is in this datum, it has signed the transaction. So you have to make sure that only the owner of the collateral can burn. We are not liquidating now, we are just burning. So it has to be the owner. We get the stablecoin minted amount, same exact as we just did. Then we check we start with the checks. Now we have the information we need. We have the collateral datum. We have the stablecoins minted amount. We can start checking. I mean, we already did the first check. We already did the first check, the owner's signature, but here we're going to do 2 more. So one check is that the burn has to be negative. So if we are burning, the stablecoin minted amount has to be negative. And that the amount of stablecoins burned has to match the amount that we stated in the collateral datum. You cannot mint more, you cannot burn more or less than the amount that was minted to generate that collateral. So we check that, same as we did in the other case. And at the end, we just put together all the checks. We make sure that the burn is negative. We make sure that we burning the same the amount of stablecoins that match the datum. We are satisfying the datum, and we check that the owner is the only one that can do this. So that's all the checks for the burning case. But remember that in the collateral redeemer, we are also checking that the correct person is signing and the stablecoin amount. This seems redundant, but it's important to make sure that it cannot be used, the collateral or the minting policy by themselves. They have to be used together. And finally, we have the liquidating case. That is more of the same. So we get the Oracle rate, same as we did before. We get the collateral input, same as we did before. We parse it to get the datum. We parse it to get the amount. We get the amount of Lovelesses only. We get the amount of minted stablecoins. We are getting information. And then we start with the checks. We check that the burn is negative. This is for a specific vulnerability that don't have time to talk about. But we have to check that the burn is negative. We have to check, same as before, that the burn matches the amount that was minted. And we have to check the liquidation. What does it mean to check liquidation? Well, the maximum amount minted that we just saw the small formula, the maximum amount has to be less than the negative of the stablecoins that were minted. So in this case, the maximum amount can be like 150, and we are burning, so it's negative 30. So the negative is a positive. So we have that 150 has to be less than 30, and this will fail. So we have to make sure that the collateral's value is low enough to be liquidated. If this doesn't check, it means that the value of the collateral is above the threshold, so no one should be able to liquidate this position. And finally, we put together the checks, same as before. Liquidation, matches datum, and burn negative. And remember that in the case of liquidating, we also at the same time check that the stablecoin amount in the collateral. So a bit fast at the end, but almost right on time. Any questions? The off-chain code is a homework to go through the off-chain code. Any questions about the validators? I know it was fast, but if you have any questions, I can answer them, no problem. Okay. So, yes.
So now we should decide what to do next. I mean, the lectures are done now, right?
Yeah.
But that was all.
Yeah.
So, I mean, what about projects? Should we now give everyone 1 week or so to think of projects and then have another meeting where people can show their projects or something like that? Anderson, you were mentioning projects as well. Do you have any ideas how we should do this?
Yeah, I'm actually thinking we can have maybe we can set some based on the lessons that you've gone through. Maybe create maybe a particular project that people can maybe a set of 1 or 2 projects. Probably I'm yet to decide if it can come from you guys or people come up with their own ideas of projects that they can build. So,
I mean, we already like gave projects on the Haskell part, and I think it's nicer to like sort of like a hackathon, so
Yes.
for people to come up with their own use case. So if you have any specific motivation that you want to implement, you have like an idea that you want to implement, we could like you could present the idea and we could like assess it to say, okay, this is too crazy difficult or it's too easy or whatever. Give you some guidance on how to accomplish that or what you have to take into account, and off you go. And maybe we should have a deadline for people to like have like a hard deadline that they have to deliver the project. But I think it's nicer to do something that you are actually interested in instead of us telling you that you have to do like this specific algorithm.
Yeah, I agree. So we can give them a week to, just as Lars was saying, we can give the students a week to think through the projects, and then maybe the next week they can present. We can have a session where they can present the ideas. You can get inputs from you all, and then have maybe like a week now to build and present. Just maybe in a week's time.
Yes, so that means next week people think about it, then maybe the following Monday, I mean, not in 3 days, but in a week, I mean, in 10 days or so, we meet again at the usual time and people can, talk about their ideas and ask questions. And then they get another week, and the Monday after that, they present their projects, something like that.
Yes.
So let me just check the calendar. So we on the 15th, people could ask questions, and on the 22nd, they would present.
Yes.
Does that sound okay to you as well, Robertino, Karina?
Yeah, I think so. And if like someone, I think that it would be fine if someone has this bigger project that is going to take more than a week, they can just, I don't know.
Yes, and of course they can also contact us on, was it Telegram or whatever,
Yeah.
if there are questions like next week.
Yeah.
But I think that's okay. Then we basically skip all the fixed slots next week, and then we meet on the 15th again. But if somebody has a question in the meantime, can ask. That sounds good to me.
Yeah. Okay. Sounds good.
Yeah.
Okay.
Okay. Then have a great weekend, everyone. Thank you very much. Thank you, Robertino, for the stablecoin. You should actually start one.
maybe. Okay. Thank you, Lars, and thank you everyone for your time.
Thank you. Bye for now.
Thank you. Bye.
Bye.